I'm waiting for the, yeah, it started. Okay, so hello. Today we'll be talking about continuous latent variables. It's a continuation of the discussion that you had last time with Trajan about mixtures and expectation maximization algorithm. And in what we'll be talking today, at, at least some of the variables will be continuous. And the simplest model that we can imagine is Gaussian distribution for both the latent and the observed variables, and the linear Gaussian dependence on the variable of the observed variables on the state of the latent variables. What does this linear Gaussian dependence means is that the mean of the observed variables is dependent linearly on the mean of the latent variables, and the variance is independent on the of the latent variables, and it has a Gaussian distribution. And this model is called principal component analysis, or PCA. You probably heard of it or maybe used it before. And in the most part of this lecture, we'll be talking about PCA. Then we'll be talking about ICA, independent component analysis, and then we will talk about autoregressive maps. So first, PCA. PCA is a technique that is widely used for dimensionality reduction, lossy data compression, feature extraction, and data visualization. It is also known as Carhoon and Loewe transform, from the two guys that independently identified this method. And since two different groups of researchers ended up with this PCA, there are two different definitions of PCA. We'll be presenting the definitions, and then we will consider each of these definitions separately and deal with it. So first, the first definition is the orthogonal projection of the data onto a lower dimensional linear space that is called principal subspace, so that variance of the projected data to be maximized. The second definition is the linear projection that minimizes the average projection cost, that is computed as the mean square distance between the data points and their projection. So we'll start with the first definition, with this one. We'll talk about it, we'll see how we derive it, and then we'll go to the second one, and we'll see that we end up with the same computation. And then we'll talk about some applications and stuff. So first, the maximum variance formulation. We consider a data set of observation, xn, where n is from 1 to n, and the dimensionality of xn is d. And the purpose is to project this data onto a lower space, onto a space with a lower dimensionality, m, that is smaller than d, that is called the principal subspace, so that to maximize the variance of the projected data. So this is the thing that we are interested in. We want to project the data, but you know, any projection is it means that we are losing some information, and therefore we would like to keep that projection that will give me the most information from the data set, which means that we would like to have the maximum variance of the data, of the projected data, of course, in the new space. So we have D as the space dimensionality, M as the dimension of the principal subspace, and initially we consider this value to be known. Toward the ends of this lecture, we will see that applying Bayesian treatment, we can identify the value of M automatically. But for the moment, let's assume that we know M. And UI will be the basis functions, basis vectors of the principal subspace. So we have M such vectors because we have dimensionality M. So we will have M such basis vectors for the principal subspace. And the purpose is to identify these basis vectors. In the initial space, we have the mean of the data defined like 1 over n summation over xn's, and the covariance given by the matrix S being 1 over n summation over xn minus the mean squared. Okay, so it's xn minus 6 multiplied by xn minus xn minus the mean of x multiplied with xn minus the mean of x transposed. And this covariance data has the dimensionality d by d. So I don't know. If there are any issues at any moments, please open your microphones and start asking what you didn't understand. So we will start with PCA with only one-dimensional principal subspace. So the purpose of this first objective is to project the data onto a line, because this is what one-dimensional principal subspace means. Okay, so if M equals to 1, it means that we have U1, which is the basis vector for this principal subspace. So we need to identify the value of U1, the parameters of U1. So in this graph, we have the points that are the red points, and we need to identify the direction of U1 and also the offset from the origin. And without loss of generality, we will consider U1 to be normalized, because we're not interested in the magnitude of U1, but we're only interested in its direction. So we only need to know what is the orientation and offset of this U1. And now, to find out this information, what we need to do is first to project the data that we have onto the U1 basis vector, and in this case, each point xn will be projected onto the scalar U1 transpose multiplied by xn. And if we do that, then the mean of the data and the variance of the data, of the projected data, will transform using this formula for the mean and this formula for the covariance. Now, if we take a look at this equation, it means that we can try to do something like this: U1 transposed multiplied by xn minus the mean, and this is squared, which means that we will have U1 transposed multiplied by xn minus the mean multiplied by xn minus the mean transposed multiplied by U1. Okay, because we need to multiply this term with its transposition, and if we have a product A multiplied by B transposed, you know that is B transposed multiplied by A transposed. And this is why it's reversing the order here. This one from here to here is the covariance matrix S, and therefore this the covariance in the new on the covariance of the projected data, so the covariance on the principal subspace, will have this formula: U1 transposed multiplied by S, the covariance from the initial space, multiplied by U1. And now what we want to do is to find the value of U1, so that the variance of the projected data to be maximized. So since the variance of the projected data can be written like this: U1 transpose multiplied by S multiplied by U1, we need to find U1 that will allow me to maximize this value. Under the constraint that U1 is normalized. So U1 transposed multiplied by U1 equals to 1. And this is solved using Lagrange multipliers. You saw this when I presented SVM, because we had to do something similar. So it's the maximization of this element with respect to this constraint. So we have lambda 1 multiplied by 1 minus u1 transposed multiplied by u1. When we want to have, so it's equation of second degree here. So if we want to find the maximum, you have to derive it and set it to set the derivation with to 0. And when we derive this, it will come 2 multiply with s u1 plus lambda 1. This is constant, so disappears, and this is u1 squared. So again, you have this minus from here multiplied by q2 u1. And this is the derivative of this term. We have to set it to 0. And now what we will have is su1 equals to lambda 1 u1. We have these two that is here and here. So we can put it if you want, but then this is the equation that we end up with. So when we derive with respect to u1 and set the derivative with to 0, we get this equation as u1 equals to lambda 1 u1, which means that u1 must be an eigenvector of the covariance matrix S corresponding to the eigenvalue lambda 1. Now, there is another thing that we can do. We can multiply this equation with u1 transposed to the left. So if we start from here and multiply with u1 transposed to the left, it means that in here we will obtain u1 transposed multiplied by s multiplied by u1 equals to lambda 1. Lambda 1 is constant, so if I have something like this, since lambda 1 is constant, this is equal to lambda 1 multiplied by u1 transposed multiplied by u1. And since we have normalized vector, it means that this is equal to lambda 1. So what we need to do is to find that u1 that will lead me to maximize this value. But this value is equal to lambda 1. And therefore, if we want to maximize the projected variance, what we need to do is to maximize the value of lambda 1. But we saw that lambda 1 is an eigenvalue for S. And therefore, since we want to maximize it, it means that lambda 1 is the maximum eigenvalue of S. Okay? So if we want to identify the one-dimensional principal subspace of a data set, all you have to do is to identify the maximum eigenvalue from the of the covariance matrix of the data set, and then since you have the maximum eigenvalue, you obtain the corresponding eigenvector, and that corresponding eigenvector is the principal subspace of the data. This is what happens if we only need a one-dimensional principal subspace. However, if you want a multi-dimensional, an m-dimensional subspace, okay, because this is what we are trying to identify, the additional principal components can be found iteratively or incrementally by maximizing the projected variance among all the directions orthogonal to those already considered. So first we identify lambda 1, and then we consider all the data that is orthogonal on lambda 1, and we repeat this action to get lambda 2 and then lambda 3 and so on. So we do this iteratively and obtain all the values of m that we are interested in. Any questions? So to do PCA in m-dimensional principal subspace, first the m-dimensional optimal linear projection space will be defined by the eigenvectors U1, Um of the data covariance matrix S, corresponding to the m largest eigenvalues lambda 1 to lambda m. The proof is done by induction. You start with only one dimension and then prove that if you have n eigenvalues, the next eigenvalue, or if you have a space with n eigenvectors, the next eigenvector that you add will be the one that maximizes what is left of the data. So PCA algorithm, it's a simple algorithm. First, evaluate the mean of the data. Once you get the mean of the data, you have to evaluate the covariance matrix and then find the m eigenvectors of S corresponding to the m largest eigenvalues. So you simply need to decompose S in eigenvalues. And this decomposition can be done in 3 different ways, as you studied in advanced maths. I think you did it, Mene. Did you do this at Mene? Do you still hear me? Do you remember what you did in the class Mene? Methodic numerical methods? Okay, so you can do it in 3 ways: by full eigenvector decomposition for a matrix which has the complexity O of d to the third. You can do it using what's called power method, and it will have the complexity m multiplied by d square, where m is the dimension of the principal subspace. Or you can derive it using the EM algorithm, and I'll show you towards the end of this lecture how to derive it. So this is about the maximum variance. Now we'll go to the second definition of PCA, which involves minimum error formulation, and it is based on projection error minimization. And we consider first an orthonormal set of d-dimensional basis vectors, UI. So we have the d-dimension data. We also consider a d-dimension basis functions. So since they are orthonormal, it means that UI transpose multiplied with uj is delta ij. So it is equal to 1 only if I equals to j, and is 0 if I different than j. Now, if I have these basis vectors, it means that each data point xn from the initial space can be represented exactly in the new space defined by these basis vectors in the following way. So xn from the initial space, it will be a summation over all the dimensions, because we have d basis vectors, multiply with the alpha ni, xn is the summation over all the dimensions of alpha ni multiplied with ui, where ui is the basis vector and alpha ni is simply the projection in the initial space of the point that we are interested in, this n, from here, on the basis vector that we are talking about, ui. So if we want alpha and j is xn transposed multiply with uj. So it's the projection of xn on the basis function basis vector uj. And this is how we can exactly represent the value of xn in this new space represented by the basis vectors that we obtained, ui with I from 1 to d. And now what we are planning to do is to approximate this data. So the goal is to approximate this data using a restricted number of variables m smaller than d. So out of these basis vectors ui, I will not use all of them. I will only use m out of d. So the purpose is to use m such basis vectors so that to represent approximately this value of xn. The m variables that we'll be using correspond to the projection of the data set onto a lower dimensional subspace called principal subspace. Now, if we want to approximate the value of xm, we'll be using a formula that looks like this. For the m values that I'm allowed to use, I will use Zni, which represent the value, the real value of the point on those directions that I am allowed to use. For all the other directions from m plus 1 to d, I will use a single value that doesn't depend on n. In here you can see that the representation for those m dimensions that I'm allowed to use depend on the value of n, so depend on the point that I'm trying to project. However, in the other directions, so from m plus 1 to d, this value of bi doesn't depend on the point anymore. Okay? So for the first m basis vectors, I will use some values that depend on the point, and for the rest of the dimensions, I will use a single value for all the points that will somehow express what's happening in those dimensions. So Z and I depend on the particular data point, while BI are some constants. And the purpose is to identify first UIs, and then ZNIs, and then BIs, so that to identify the principal subspace and the error. The error that we said that is a distortion error that is computed as the square difference between the point that I want to project and its projection or its approximation that is computed using this formula. Okay, and we would like to find UI, ZNI, and BI so that to minimize the value of this error. Any problem till now? Do you have any question? Okay. When I do the minimization with respect to Z and J, I will get that Z and J equals to the projection of the point that I'm interested in on that basis vector. So actually, if you remember from the first representation, if I want to exactly represent xn, I would have a summation from 1 to d of alpha nj uj, where alpha nj was nothing more than xn transposed multiplied with uj. And what we get after minimization of the error with respect to Z and J is that Z and J actually equals to alpha and J. So for those directions, for those m dimensions that I'm allowed to use, we will use exactly the projection of the point on the basis vector that we get. Now, when we do the minimization with respect to Bj, we will get that Bj is the mean of the point of the data set projected on those basis function for all the basis function that I'm not allowed to retain. Okay? So for all those dimensions from m plus 1 to d that will not be part of the principal subspace. Having these values for Z and J and Bj that were obtained using the minimization, it means that the error, or the difference between xn and its projection xn tilde will be in fact this formula, because when we have the exact value of xn that is given here, it means that we have the summation from 1 to m of alpha nj uj plus summation from m plus 1 to d of alpha nj uj. And now, since we identify bj and z and j, it means that when we do the difference minus summation of from 1 to m alpha nj uj minus for all the other dimensions from m plus 1 to d of x mean multiplied by uj, which is this part, multiply again with uj. So this is transposed and multiply with uj. So actually what's happening, this part and this part are cancelled out, and the error will be for these two sums. So it's in the space from m plus 1 to d. You can see here dimensions. Sorry, what's happening? So come on, stop it. Okay, I fixed the problem. Now we can continue. So it will be the difference between alpha nj and this product, x mean multiplied with uj. So it will be xn minus the mean multiplied with ui multiplied with ui. Okay, so this term is this term, and alpha nj equals to this. So xn transpose multiplied with u. The mean multiplied with u again is transposed, and therefore we have this this equation xn minus the mean transposed multiply with u1, this part, multiply with u1 and ui again. So what we can tell from this equation is that the error that we have lies in the space that is orthogonal on the principal subspace, because you see that the error is on the dimensions that I'm not allowed to retain for the principal subspace, so on the dimensions from m plus 1 to d, and it's a linear combination of ui's that correspond to these dimensions that I'm not allowed to use. And since the basis vectors that I have chosen are orthonormed, it means that the value of the error is orthogonal to the principal subspace in the other on the other dimensions. So what this means actually is that xn tilde must lie in the principal subspace, but we can move it freely in this subspace, and the minimum error is given by the orthogonal projection, because if I have the distance from a point to a subspace, the smallest value for this distance will be when we have exactly the projection of that point on the subspace. So since we know that the minimum error is obtained when we have the orthogonal projection of that point onto the principal subspace, it means that we can rewrite the value of j as being 1 over n summation from 1 to n, summation on all the dimensions that are not kept for the principal subspace out of the error, which means the projection of the points, of the individual points on these basis vectors that we're not keeping for principal subspace, minus the projection of the mean on the same vectors. So actually in here, we can do again what I showed you earlier, and we will get UI transpose multiplied by S multiplied by UI, but only for those dimensions that are not kept in the principal subspace. So the value of J will be equal to this summation from n plus 1 to D out of the UI transpose multiplied with the covariance matrix multiplied with UI. And now the purpose is to minimize the error. So this is the error, what we computed. This is the value of the error. And J is minimized with respect to UI under the orthonormal constraints UI transpose multiplied with UI equals to 1 is solved again using Lagrange multipliers, and again we get the same equation as before, SUI equals to lambda I UI. Since we want to obtain the minimum error, it means that what we want to keep for the dimensions where the error lies is the smallest eigenvalues, alpha i's, associated with the covariance matrix S. So basically what that means is that distortion is the summation from n plus 1 to D out of the smallest lambda i's, eigenvalues, for the covariance matrix S. So this is how we obtain the minimum value of J. Minimum value is obtained by selecting the eigenvectors to be corresponding to the D minus M smallest eigenvalues of S, which means that if these are the values corresponding to dimensions from n plus 1 to D, the rest of the dimensions, the one with the highest M eigenvalues, correspond to the principal subspace. Okay, so the principal subspace is spread out by the eigenvectors corresponding to the M largest eigenvalues from the covariance matrix. And now, if we want to approximate the value of xn, we have the formula xn tilde equals to the summation from 1 to m of xn UI transposed UI multiplied with UI plus the summation from n plus 1 to d of the mean that is projected on the UI multiplied with UI. But this can be also written as being the mean. So in here, I will write this as being the mean plus xn transposed minus the mean multiply with UI and then again multiply with UI. So if I'm writing this for the dimensions from 1 to m, it means that I can separate these two sums into only one, this sum into two sums. So I will have 1 over m, the mean multiply with UI multiply with UI plus summation from 1 to m of xn transposed minus the mean transposed multiply with UI and multiply again with UI. This part, with this part, it's actually the mean of the data, okay? Because it's the summation of the mean from 1 to m plus the summation from m plus 1 to d out of the mean. So these two together Okay, so if I have a summation of these two, it means that I will get the mean. And therefore, to retain the value of xn tilde, I can obtain the mean that will be the same for all the points. And for each individual point, instead of keeping d values representing their exact position on each of the dimensions, I will only keep m values representing the difference between the point, the individual point xn, and the mean on each of those m dimensions from the principal subspace. Is it clear? Can you still hear me?
Yes, we can hear you and it's clear.
Great, thank you. And now, since we ended this part, we get to some applications of PCA. One of them is lossy data compression. We start from a dataset composed by one image and multiple copies of that image that have been modified by random displacement and rotation. And the purpose is to compress this dataset. Initially, the data, the images have 28 pixels by 28 pixels. So the dimensions, the number of pixels, which means the number of features, is 784. And we would like to compress this data set. We know that it will be a lossy compression, considering the value of m that is much smaller than d. So what we will be doing, first we derivate the covariance matrix. So first we get the mean, and the mean will be something like this. Then we compute the covariance matrix. Once we have the covariance matrix, we get the eigenvalues of those matrix. The eigenvalues will correspond to some eigenvectors in the d-dimensional space. And if the eigenvectors are in the d-dimensional space, it means that we can represent these eigenvectors as images of the same size as the initial images from the dataset. And in here, we have the top four eigenvalues here. And below each eigenvalue, we have the corresponding eigenvectors. Okay? So we have the mean of the dataset, and this is the eigenvector corresponding to the highest eigenvalue, the eigenvector corresponding to the second eigenvalue, and so on. In here, the blue values are positive values, the yellow values are negative values, and the white values are 0. Okay? And now, having these eigenvectors and eigenvalues, we can represent the data as we saw before, as the mean plus some differences between the points and the mean. But first, let's see. Here we have a graph representing the values of the eigenvalues. So the highest eigenvalue is 3 point something, 3.4, I think, multiplied with 10 to the minus 5. The second one was somewhere around 1.5 multiplied by 10 to the fifth, and so on. And if we have these eigenvalues, we can plot the value of j, the distortion that we are interested in minimizing, because since we are doing lossy data compression, we would like to lose the fewest information as possible. So there will be a threshold. The more eigenvalues I will keep, or eigenvectors I will keep, the less information I will lose. So the less lossy will be the compression. So in here there is plotted the value of j according to how many lambdas or how many eigenvectors are kept in the principal subspace. And we can see that if we get around 250 or something around here, the error starts becoming very, very small. So if we keep these eigenvalues and their corresponding eigenvectors for M, for the principal subspace, it means that all the rest will be the error that we will get as data compression, and we will approximate the points from the data set xn as being the mean of the data that we saw earlier, plus what is the variance, let's say, or the difference between that individual point and the mean for each of the m dimensions that we kept for the principal subspace. And therefore, for each data point, we have replaced the d-dimensional vector xn with an m-dimensional vector having the components xn transposed ui minus the mean transposed multiplied with ui. And for our data set, if we keep only one dimension, so if we project the data onto a one-dimensional principal subspace, we get something that is very similar to the mean, because the mean will have a high importance. If we keep 10 dimensions, then the representation will be somehow closer to the original value or original picture, but it still has some elements from the mean. If m equals to 50, it starts looking like the original picture, and if we retain 250 dimensions, the picture that we get is almost similar with some artifacts, because you can see that in here the area is not exactly white as it is in the original picture, but is somehow similar to what we have in here. Okay. And we kept only 250 dimensions, so m equals to 250 dimensions, while d was 784. So we only kept 1/3 of the data to represent all the data from the dataset. Do you have any questions? Okay. The next possible application of PCA is data preprocessing. And the purpose is to transform the data set in order to standardize some of its properties. And why would you do that? Because once the data is standardized, you can apply some pattern recognition algorithms that will tell you more information about the data. This data preprocessing is usually done when the original variables are measured in various different units. For example, if we have something in meters, something one dimension in meters, another dimension in kilometers, another dimension in I don't know, currency and so on, or when we have significant different variability. And an example is the Old Faithful dataset. I don't know, maybe Tran told you more about this dataset. Do you know about it? It represents the time between eruptions versus the duration of an eruption. And you know, there are around 98 years, I think, between consecutive or 40, and I don't remember exactly, between consecutive eruption of this volcano, Old Faithful. And the duration of one eruption is like a couple of days. So the dimension, the scales of the two dimensions is very different. And this is Old Faithful because it is very precise, let's say. one can predict when will be the next eruption. And to do this data preprocessing, usually the dataset will be normalized to give zero mean and unique covariance, so that different variables become decorrelated. And for this task, we can use PCA. Again, we start from the eigenvector equation, covariance multiplied with U equals to U multiplied with L. L is a diagonal matrix having on the principal the diagonal the elements lambda I, so the eigenvalues. U is a D by D orthogonal matrix with columns given by UI, so by eigenvectors. And now, to do the standardization, we will transform xn to yn, operation that is called widening or sphering, and yn will be L to the minus 1 over 2, so 1 over S squared T of the elements Lii, because I told you that L is a diagonal matrix, and since it's diagonal, you can compute the S squared T of the elements of from the diagonal, multiply with U transposed that I told you that is given by the columns of UI, multiply by the difference between the point and the mean of the data set. And it's easy to see that yn has zero mean, because if we're applying a summation over all the points, these elements will go in front of the summation, and what we will do is the summation of xn minus the mean. This one goes out of the summation, and we will have summation over xn minus n multiplied by the mean, and the mean is 1 over n summation of xn. So if we reduce the n's, we will get summation over xn minus summation over xn, which equals to 0. To identify, to see the what's happening with the covariance matrix, we'll have to multiply yn with yn transposed. And when we multiply this, we will get this situation. This one is the covariance matrix. And we will get L to the minus 1 over 2 multiplied by U transposed multiplied by S multiplied by U multiplied by L to the minus 1 over 2. These three elements equals to L. Okay. Because if we multiply with U here and here, we will get sorry, here, not the other way. Then we will have U multiplied by S multiplied by U transposed multiplied by S multiplied by U equals to U transpose multiplied by U, which is an orthonormed matrix. So it's identity matrix multiplied by L. So this is why U transpose multiplied by S multiplied by U equals to L. And now we have L to the minus half multiplied by L multiplied by L to the minus half. And this is identity matrix, because again, it's a diagonal matrix and we can do the computation. Do you have any question? So if we have original data, you can see that the scales are different. So the first step is to obtain the same scale for both dimensions, and we also obtain the main directions of the data, so the principal subspace in 2 dimensions, and then the result of whitening, what I showed you earlier, is like this. And you can see that the data were possibly to be clustered like this. And again, these clusters are obvious again in the second representation. And now there is an interesting comparison between PCA and Fisher's linear discriminant that we presented earlier. If we consider, so this is PCA, this is Fisher, and you can see that PCA that is unsupervised chooses the direction of maximum variance. So it chooses a direction that will spread out the data set as large as possible, while Fisher takes into account the class labels, which is supervised, and draw the classifier like this. If we are to draw a classifier based on PCA, you can see that is only very, so it should be perpendicular on the magenta line, and it's very the deviation from Fisher's linear discriminant is very small. So even that it's an unsupervised method, it does a great job of at capturing the covariance sorry, the variance of the data. Do you have questions? Okay. Another application of PCA is visualization. Do you remember this image where we had a combination of oil, water, and gas? And I told you that the data set has 10 dimensions, out of which only the 6th and 7th dimension are represented. And when I presented you this picture, the problem was, how can we classify this point? Now, what we are interested in is for the same data set to try to represent it in such a way that can be visualized. So either in in 2 dimensions or 3 dimensions. So we would like to project this data either on 2-dimensional principal subspace or a 3-dimensional principal subspace. So that a data point xn to be plotted at Cartesian coordinates given by xn transpose u1 and xn transpose u2, or if you want in 3D, we will also have xn transpose u3, where u1 and u2 are the eigenvectors corresponding to the largest and second largest eigenvalues. Again, if we have 3-dimensional representation, u3 will be the third highest eigenvalues from the covariance matrix. And if we have that, then when representing the data points, we will see something like this. So out of this representation, where we don't get much of the structure of the data, we get to a much easier to interpret representation, considering the projection, the projection of the data for the visualization. Now, these are some applications that PCA proved to be useful at. There is another thing that might be interesting. There might be situation where the number of data points n that we have in the data set to be smaller than the dimensionality of the data d. And therefore, it means that those n data points will define a subspace with the dimensionality n-1. So if we have this, it means that in the covariance matrix from the D space, we will have at least D minus n plus 1 eigenvalues that will be equal to 0. So if we know that this is the case, it means that is computationally infeasible to extract the eigenvectors from the original covariance matrix, because that will be O to the we will have complexity d to the third, which is much higher than what we would like to obtain, considering that we will only need to find out at most n-1 such eigenvalues. So we can do a trick so that in order to work in the d by d space, to work in the n by n space, and then to derive the eigenvectors corresponding to the principal subspace. So how can we do that? First, we denote as being x the matrix that is n by d, so the number of the samples multiplied by the dimension. That is centered. It's a dimensional centered matrix in the sense that the nth row will be given by the difference between the point and the mean of the data. Now, the covariance matrix, considering this, will be 1 over n multiplied with x transposed multiplied with x. And we can derive the n-1 non-zero eigenvectors working with the n by n matrix instead of d by d, because I told you n is smaller than d in this case. And this is how we do it. First, we write the equation, and the equation was S multiplied with U equals U multiplied with L. This is the covariance matrix. So 1 over n x transpose multiplied with x multiplied with the basis vector from the d-dimensional space equals to lambda I ui. And now we multiply this with x to the right. So we will write an x here and then an x here. So, sorry, to the left, not to the right. So we might multiply by x here and here. Since lambda is a constant, goes in front, so we will have x multiplied by x transposed. This part we will group together because we will have it in the other side as well, as you can see in here. And it means that if lambda I is a eigenvalue for the covariance matrix S, it will be also an eigenvalue for the matrix X multiplied with X transposed. And therefore, Vi, that it's denoted, this term is Vi, will be an eigenvector for this matrix. But since X is n by d, X multiplied with X transposed is n by d multiplied with d by n. So it will result into a matrix that is n by n. So Vi that we have in here, that is X multiplied with Ui, will be an eigenvector for the n by n matrix. Now we multiply again to the left with X transposed. So we put an X transposed in here and an X transposed in here. And what's happening now? We get, again, since lambda I is constant, it will go in front. And in here we will have X transposed multiplied with Vi. And therefore we will keep this separate in here. And since we add X transposed to the front, we will have 1 over n X transposed multiplied with X, which is exactly S. So this is S. Multiply with X transpose Vi equals to lambda I X transpose Di. So basically X transposed multiplied with Di is an eigenvector of S corresponding to the eigenvalue lambda I. So this is actually the eigenvector that we were interested in, Ui here, because you know, if Ui corresponds to lambda I and this term corresponds to lambda I as well for the same matrix, it means that Ui equals to X transposed Vi. So basically what we're doing, we're getting the n by n matrix, we decompose it with, I don't know, either power method or whatever we would like to have, or the direct method, full eigenvector decomposition. We extract the eigenvalues from there. Having these eigenvalues, we can derive Vi as being the eigenvectors corresponding to the eigenvalues lambda i's, and then we multiply it by X transposed to the left in order to obtain the eigenvectors of the initial matrix, covariance matrix S, because lambda i's are the same. Now, if we want to obtain normalized eigenvectors for S, it means that we need some rescaling to do, and therefore UI that we were interested in is 1 over sqrt of n multiplied with lambda I multiplied by this X transposed multiplied with Vi. And this is how, instead of computing the eigenvectors in the d by d matrix, the original covariance matrix, we computed the same eigenvalues and eigenvectors, but using a n by n matrix, which is much smaller than the initial d by d matrix. Do you have questions? Okay. Now, we will continue with probabilistic PCA. What we talked about PCA till now was based on a linear projection of the data onto a subspace of lower dimensionality. But in the same time, PCA can also be expressed as the maximum likelihood solution of a probabilistic latent variable model, which leads to the probabilistic PCA. And this probabilistic PCA has some advantages. One of them being that we can derive the EM algorithm for PCA so that to compute the decomposition in eigenvectors efficiently. Another thing is that it allows us to deal with missing values in the data set. We can use mixture of probabilistic PCA models. And another important thing is that we can apply the Bayesian treatment of PCA, which allows us to identify automatically the value of M, as I told you in the beginning. Moreover, we can apply probabilistic PCA to classification problem. We can run it generatively to get samples from the distribution and so on. So it has some advantages, but it involves a little more computation because you know that you would need some probabilities and you'll have to derive them to compute them and so on. So probabilistic PCA is a constrained form of the Gaussian distribution in which the number of free parameters can be restricted while still allowing the model to capture the dominant correlation from the data set. And let's see how we deal with it. So first of all, we consider an explicit latent variable Z corresponding to the principal component subspace. And we said that we have a linear Gaussian dependence. So it means that Z will be Gaussian, just as the distribution from the original space. So we will have a Gaussian prior distribution P of Z over the latent space that will be with zero mean and identity matrix covariance. And also we will have the Gaussian conditional distribution P of X given Z. That will depend. I told you that we have a linear dependence on the latent variables. So we have a linear combination of Z that we have for the latent space. And we have Gaussian noise. So the covariance matrix is independent on Z. And it has a Gaussian form. So we have sigma squared multiplied by E. So Z is an m-dimensional Gaussian latent space. W is a D by M matrix corresponding to the latent space. We need to find this out. Mu is a D-dimensional vector. We will see that we use this mu in order to allow the distributions to not have zero mean. So to be able to impose there any other mean that we would like to have. And sigma square is a scalar governing the variance of the conditional distribution. As I told you, it doesn't depend on Z. And we will use a generative view. So we know that Z comes from a Gaussian distribution. So first of all, we will sample a value of Z. Let's say it's Z hat. And then starting from this distribution, we will sample the observed variable conditioned on the latent value. So we know that have p of x given z, but now we know the exact value of z, and is z hat, and therefore we have this Gaussian distribution that is centered in here, and we also know that for x we have this formula wz plus mu plus epsilon. So it means that the mean of the original data mu will be the distribution of p of x given z hat minus this value z hat multiplied with w, and this is how we get the original mean of the data mu. And therefore afterwards we will sample from here. So the value of x will be the distribution that is centered in mu in this position and has this Gaussian noise. So the d-dimensional observed value x is defined by the linear transformation of the m-dimensional latent variable z hat plus the additive Gaussian noise. So this is how we identify p of x. First sample z hat, then condition the value of x depending on z hat, and then we finally obtain the distribution for p of x. And again, z is the m-dimensional Gaussian latent variable. W is the latent space. Epsilon is the zero mean sigma square covariance noise, Gaussian noise in the d-dimensional space. And I told you that epsilon and z are independent. And mu is a parameter vector that permits the model to have non-zero mean, because otherwise I would have had to place mu in here, and the center of the distribution being in here, I wouldn't be able to move from here to a different place. And this is why we added the value of mu, so that to be able to have distributions that are not centered in the origin. And now the purpose is to estimate the parameters W, mu, and sigma square using maximum likelihood. And therefore, we need the expression of P of x. And we will get this as using the sum and product rules of probability. Because since we have continuity, we have integral of the P of x given z multiplied by P of z. Since P of z is a Gaussian centered in the origin and with identity covariance, so is isotropic, it means that P of x that is obtained from the product of two Gaussians will also be a Gaussian, depending on the mean of the data and on the covariance matrix C that is defined as being W multiplied by W transposed plus the noise sigma square. And now, given a data set x of xn, so let's think a bit. Xn depends on what? Depends on the latent variable zn that corresponds to xn, depend on the noise and on the mean that are from the original space, and also depends on the parameters w that represent principal subspace. So given xn of observed data, the log likelihood is logarithm of p of x given mu w and sigma square, and which is the summation of a logarithm of p of x given w, mu, and sigma square. It has this formula, and when we set the derivative with respect to mu equals to 0, from here, so these terms disappear, it remains only this one, and we obtain that the value of mu, it will be nothing else than the mean of the original data. Once we substitute back in this formula here, we will get a simplified version of this likelihood is minus n over 2, okay, d multiplied with logarithm of 2 pi plus logarithm of the determinant of c plus the trace of c minus 1. This is again, since mu is the mean, it means that we have the covariance matrix in here, multiply with c to the minus 1. So we will have the trace of c to the minus 1 multiplied with s. And fortunately, this solution represents the unique maximum. This was the derivation with respect to the value of mu. The derivations with respect to W and sigma square are more complex, but have an exact closed form solution that looks like this. The W maximum likelihood will be UM multiplied with LM minus sigma square. This one, it will be diagonal matrix. So we have S squared T of it. We can do that. Multiply with R. R is an arbitrary orthogonal matrix. R comes from rotation, and we'll see what's happening later on. UM is the matrix whose columns are given by the eigenvector of S, corresponding to the m largest eigenvalues. LM is the diagonal matrix given by the corresponding largest eigenvalues, lambda i's. And again, R is an orthogonal matrix. So if we have this formulation, the maximum likelihood solution for sigma square will be sigma square maximum likelihood is 1 over d minus m summation of over lambda i's for all these dimensions that we're not keeping. So actually what is this is a mean of all the eigenvalues that correspond to the space that is not kept as the principal subspace. So the smallest d minus m eigenvalues are averaged, and this average is the sigma square maximum likelihood that we obtain. R, as I told you, is a rotation matrix in the m by m latent space, because we have Gaussian distribution, which means that the data will be evenly distributed in all the directions, and therefore if we have a rotation, then we must end up over the same data basically. So if W will be substituted back in the equation for C, W multiplied by W transposed plus sigma square, let's see what we get. So it's UM multiplied by LM minus sigma square, sorry, this is supposed to be sigma, not delta. So it's sigma squared multiplied with I to the S squared T multiplied by R multiplied by R transposed multiplied by LM sigma squared I to the 1 over 2 multiplied by UM transposed. I didn't wrote transposed in here because since we have diagonal, the transposition will be the same. Now, this is an orthogonal orthonormed matrix. So R by R will be equal to identity matrix. So this one will disappear. And we will actually have UM multiplied by LM minus sigma squared I it's S squared T from here multiplied with S squared T from here. We will not have any power left. Multiply with UM transposed. If R equals to I, so identity matrix, it means that the columns of W in here, okay, so if this disappears because it can be identity matrix, it means that the columns of W are the principal component eigenvectors, UIs, scaled by the variance S squared T of lambda I minus sigma square. Okay, because in here I will have S squared T of lambda i's minus sigma square, and UIs will be the corresponding eigenvectors for lambda i's. Now, let's suppose that we have an orthogonal vector that is a norm vector that has the property V transpose multiplied with V equals to 1. And what's happening? If V is orthogonal on the principal subspace, so it means that V transpose multiplied with U equals to 1. It means that when we compute this value, which means that I'm adding a V transposed in here, since this initial product is equal to 0, this will disappear. Sorry, what I drew in here is W multiplied with W transposed. Okay, so if V transpose multiplied with U equals to 0, it means that this term here disappears, and the variance that we get if V is orthogonal on the principal subspace is simply what we get in here. So it's sigma squared. So for the dimensions that are not kept as principal subspace, we will predict average noise. Noise that you saw that is the average of the lambda i's for all the i's that are not kept in the principal subspace. However, if V equals to UI, it means that, sorry, I have a correction to make here. So, damn it. So V transposed, V multiplied with V transposed is this part. If we are trying to do V transposed multiplied with C, it means that we need to do V transposed multiplied with this, which means that we have V transposed multiplied with this. Now, if V equals to UI, it means that since UM is an orthogonal matrix, it means that it will remain only one line from here, the line corresponding to the UI. And in here, instead of LM, we will have lambda I. So what we get is when we multiply this, we will get lambda I from here minus sigma square plus sigma square from here. Okay? Because when we multiply V transposed multiply with C multiply with V equals to V transposed multiply with W multiply with W transposed multiply with V plus V transposed multiply with sigma square multiply with I multiply with V. This goes in front, this doesn't matter, and V transpose multiply with V equals to 1 as we showed in here. So if V transposed equals to UI, from this term we'll only get lambda I minus sigma. And from this term we will only get from the second term we will get lambda squared. So when V equals to UI, we will get simply lambda I minus sigma square plus sigma square equals to lambda I. So on the model will correctly capture the variance of the data along the principal axis of the principal subspace and approximates the variance in all the remaining directions with a single average value lambda squared that is simply the average of all the other lambdas corresponding to the space orthogonal on the principal subspace. Now, the values of W and sigma square can be determined using algorithms like conjugate gradients or expectation maximization. But if we do that, at the end of EM, the columns of W might not be orthogonal, and therefore we will have to post-process W. And now we will see how can we derive the expectation maximization. So, but before, there is another thing that we need to think about. In conventional PCA, we have a projection of points from the d-dimensional data space onto the m-dimensional linear space. In probabilistic PCA, we have a mapping from the latent space to the data space. But since we want PCA for visualization, for data compression, and so on, we don't need this mapping. We actually need the reverse mapping, because what we would like to do is to get from a higher space to a smaller one, not reversed. So basically what we need here is to reverse the mapping that we get from probabilistic PCA, and therefore points X from the data space can be summarized by its posterior mean P of Z given X, which is a Gaussian that depends on 1 over M, where M is this value, multiplied by the W transposed, multiplied by the difference between X and the mean, 1 over sigma squared multiplied with M. M is the M by M matrix corresponding to the principal subspace, and will be W transposed multiplied with W plus sigma squared multiplied with I. The mean of this data, so expectation of Z given X, will be M to the minus 1 multiplied with W maximum likelihood multiplied with X minus the mean. We saw this a bit earlier. Covariance will be sigma squared multiplied with M, is independent on X, and therefore the projection will be X, the expectation of Z given X multiplied by W plus the mean. So this is how we get the projection that we are interested in, the correct mapping from the data space to the principal subspace. Now we will get to the EM algorithm for PCA. Is advantageous from the computational point of view because it's iterative and we're not working directly with the covariance matrix. It can also be used when some values are missing or for mixtures of models. But in order to work with it, you saw last time that it needs the complete data log likelihood. So we cannot work with the probability of X given Z. We need to work with the joint probability of X and Z, which means that we will have logarithm of probability of X given Z plus logarithm of probability of Z. And we've also seen in the previous slides that mu equals to the mean of the data, and we will use this information to simplify things. So actually what we have to compute is this ugly formula. I won't insist on it. We will initialize W and sigma square. In the E step, we will have to evaluate expectation of Z and expectation of Z multiplied with Z transposed using the old values for W and sigma square. So we'll have M to the minus 1 W multiplied with Xn minus mean as expectation of Zn. And expectation of Zn multiplied with Zn transposed is sigma square M to the minus 1 plus the product of expectation of Zn that we already computed in here, multiply with expectation of Zn transposed. Because these are the terms that we are interested in. You can see this is the expectation that we need. And these are the plus the weights the W and sigma from here. Okay, in the M step, we maximize the expectation of the complete data with respect to W and sigma square. So we get W new and sigma square new. I would ask you to take a look on W new, because we will come back to this formula. So it's the summation of xn minus the mean multiplied with expectation of Zn multiplied with expectation of Zn multiplied with Zn transposed. When we will have the task of Bayesian treatment, in here we will get a new term that will help us automatically identify the value of M, the dimension of the principal subspace. So first we estimate these expectations, then we maximize with respect to W and sigma square to get new values for W and sigma square. Then we check for convergence, and if it didn't converge, then we start all over with the next expectation step and maximization step. If sigma square tends to 0, then EM approach corresponds to standard PCA. And to easier visualize what we have to do, we will define x tilde as being a matrix of n by d given by the differences between the points and the mean. And we define omega as being a d by m matrix given by expectation of Zn. And now with these notations, we'll have omega as being W transposed old multiplied with W old to the minus 1 multiplied with W transpose old multiplied with x tilde. Have you seen this formulation before? This is the pseudo inverse, or Penrose inverse, pseudo inverse. So it represents the orthogonal projection of the data points onto the current estimate of the principal subspace. And in the maximization step, we will have x transpose multiplied with omega transpose multiplied with omega multiplied with omega transpose to the minus 1. And this is basically the re-estimation of the principal subspace, minimizing the squared reconstruction errors in which the projections are fixed. So if we have some initial spaces, some initial points in the space, we have this initial estimation of the subspace. We are doing the projection. We fix the projection on the principal subspace, and now we try to minimize the distance between the points and their projection. So we re-estimate the subspace. Then we project again the data on the new subspace, on the new orientation of the subspace. Then we re-estimate the subspace. And finally, when we do the projection, we will get to convergence. This is, however, a happy, happy scenario, because in reality, there will be like a lot of steps until you reach this point of convergence. Do you have any questions? Okay. The Bayesian treatment of PCA is useful to automatically identify the dimensionality of M, and it comes by not considering W fixed, but considering that there are some parameters alpha that governs the value of W. There is a different way to compute to identify the value of M by employing cross-validation, but this is very costly from the computational point of view, and is inefficient, and therefore it's easier to derive the value of M through Bayesian PCA. which again considers some Gaussian prior over the columns of Wi, and the variance is governed by this precision parameter alpha I. So we have the probability of W given alpha that has this form. And now the values of alpha i's are estimated iteratively by maximizing the logarithm of the marginal likelihood function p of x given alpha, mu, and sigma square, which is the product p of x given w, mu, and sigma square multiplied with the probability of w given alpha. As a result of this maximization, some values for alpha I are driven to infinity, and therefore, since alpha I is driven to infinity, it means that W must be equal to 0. And therefore, in this way, we are doing an effective dimensionality reduction. We identify the number of finite alpha I values, and it means that the corresponding subspace will be formed by the Wi's that correspond to the finite alpha I values. And we can also do this in between the EM steps. So the maximization with respect to alpha I will give us this formulation. Alpha I nu is D divided by W transposed multiplied with Wi. And we can interleave this maximization with respect to alpha I with the EM algorithm that we defined before. And this is why I told you to pay attention to W nu, because we add this value in the formulation of W nu, and the value of A is the diagonal of alpha i's, and it will automatically lead to also driving some alpha i's to infinity and corresponding W's to 0. So we'll actually automatically identify the value of M. And this is the difference. In here on the left, we have maximum likelihood PCA. And on the right is the result of Bayesian PCA. We have 300 data points in 10 dimensions. Sample from Gaussian distribution with 3 dimensions that have larger variance. The black squares are negative values. The white squares are positive values. And the dimension of the square is proportional to the magnitude of that value. And you can see that out of the 10 dimensions that we have, some have some small variance, like for example this one, and therefore when we do Bayesian PCA, it is replaced by zeros. In here we have large variations because we have large negative values and also large positive values. On the third column, we have mainly positive values. You can see that there are very small negative values and are not very large, like this one, positive values. So again, is discarded. On the fourth dimensions, we have huge values for negative and large values for positive values. So again, is kept and so on. And as you can see, only 3 dimensions are kept. So the Bayesian PCA correctly identifies the number of dimensions for the principal subspace. Do you have any questions related to PCA? Because from now on, we'll be talking about ICA a bit and then autoregressive maps. ICA, it's a model in which the observed variables are related linearly to the latent variables, but for which the latent distribution is non-Gaussian. And ICA independent component analysis is an important class of such models for which the distribution of latent variables factorize. So if I have multiple such variables, they will be independent one on the other. So probability of Z will be the probability of individual Zj. And as an application is the blind source separation. The problem is we have two or more people talking at the same time, and their voices are recorded using microphones, individual microphones that are one microphone per person. And the goal is to reconstruct the two individual signals separately by given only the mixed data. So this is why it's called blind source separation, because all we are given is the mixed data and we have to reconstruct the two signals independently. In this problem, the latent variables will be the original sources and the mixing coefficients. And under some assumptions, if we don't have time delay and we don't have echoes, it means that the signals received by the microphone are linear combination of the voice amplitudes. So think of a class and suppose that there are multiple, like in conferences, for example, there are multiple microphones in the same class. There is a microphone in front for the presenter, and in the Q&A section of the presentation, the second microphone or the other microphones are moved around in the room so that the questions to be heard by everyone. And in this situation, the speaking of the presenter or the one who puts the question is independent because they might start talking in the same time. And also what I hear in one microphone. So if one microphone is in the front of the room where the presenter is, and the other one is somewhere in the room, you will hear both the speaker. I mean, if both speakers speak in the same time, you'll hear them in both microphones. So therefore, the signals received by the microphone will be linear combination of the voice amplitudes, and also the coefficients of this linear combination are constant because I'm not playing with the microphone, closing it and setting away from my mouth. Now, if we consider a generative model having the latent variables as being the unobserved speech signal amplitudes, and therefore the two observed signals will be the pair O1 and O2 at the two microphones. Since the distribution factorizes, so the probability of one people speaking is independent on the probability of the other people speaking, we don't have to include noise. So the observed variables will be a deterministic linear combination of the latent variables. So we can write O is the amplitude received by the two microphones, the amplitude of the two persons that are speaking, multiply with the Z, which is the latent subspace that we need to identify. And given a set of observations, the likelihood function is a function of the coefficients Aij that we need to identify. Log likelihood maximization using gradient-based optimization will solve this problem, and it's a particular case of ICA, independent analysis. Again, the observation is that we must have non-Gaussian distribution, because you saw that in probabilistic PCA, the latent space distribution was a zero mean isotropic Gaussian. So we have the same distribution in all the directions. And therefore there is no way to distinguish between two choices for the latent variables if these two variables differ by rotation in the latent space. And therefore, for ICA, for independent analysis, the common choice for the latent variable will be 1 over pi multiplied with cosinus hyperbolic cosinus of zj. So it has this formulation. Do you have any questions? The final topic will be auto-associative neural networks. You know, most of the time neural networks are used for supervised learning, but however, they can be applied to unsupervised learning, like dimensionality reduction, to project the data onto a lower subspace and then to be able to reconstruct them. And these kind of networks are called autoencoders. And they have the same number of outputs as inputs. And we would like to optimize the weights of the network so that to reconstruct the outputs as being the inputs that are given to the network. So actually the targets that are used to train the network are simply the input vectors themselves, and basically the network will try to map each vector onto itself. But if we go through a layer that will be the principal subspace, which means that we'll have a dimension, a number of neurons that is smaller than the input data, perfect reconstruction is usually not possible. These are also called auto-associative mapping. And this is the structure. So we have a multi-layer perceptron with D inputs, D outputs, M hidden units. So a perfect reconstruction is not possible. And what we need to do is to find the network parameters W, so that to minimize the error given as the sum of square errors between the outputs that are obtained minus the inputs that were given. If the hidden units have linear activation functions, the error has a unique global minimum. At this minimum, the networks perform a projection onto the m-dimensional subspace, which is spanned by the first m principal components of the dataset, and the vector of weights which lead to the hidden units form the basis function which spans the principal subspace. There should be this observation, the vectors need not be orthogonal or normalized, because you don't have this constraint as being normalized as you have in the normal PCA. If instead of using a linear activation function, we use non-linear hidden units, then the minimum error solution is also given by the projection onto the principal component subspace. So there is no advantage in using two-layer neural networks with non-linear hidden units to perform dimensionality reduction. However, if we have multiple layers, for example, if we have 4 layers and we use the first and the third layer to use non-linear basis non-linear activation, then it means that we will map initially F1 will map the original data space into a new subspace S, which will be the principal subspace, and then F2 will do another non-linear transformation to give it to send it back to the original data space. And such a network effectively performs a non-linear PCA. So in this situation it's okay to have non-linear activation functions because with this setting we have a non-linear PCA that is done by the network. So the advantage is that we're not limited to linear transformations. However, the training of such a network involves nonlinear optimization techniques, which means that we might not end up in the global optima. And this is a risk that comes with the advantage that you might get better representations for your data. That was all for today. If you have any questions, please shoot. If there are not any questions, then thank you for your patience in looking at these complicated presentations. As I told you, this was my last presentation for the semester. Next time, you will have to present the alpha version of your project. Then Traian will teach another class, and then in the final week, again, you'll have to present the final version of the projects. Okay? See you next time. Good luck with the projects, and good night.
Thank you. Goodbye.
Thank you. Bye-bye.
Thank
Bye.
you. Goodbye.
Thank you. Nice evening.
Thank you. Bye-bye.